Hello, everybody. Hello, everybody. We're going to start our next talk, which is network-wide visibility with Linux networking and sFlow. Our speakers here today would be Neil and Ido, and they're going to be around to take questions after we finish the pre-recorded video. Enjoy.
Hello. Welcome to this talk on network-wide visibility with Linux networking and sFlow. To start us off, we have Ido Schimmel from Mellanox, now NVIDIA. And in this talk, we're going to show how the convergence on standard Linux APIs is transforming network monitoring. Ido.
Thanks, Neil. This presentation is split into two parts. I will present the first part, while Neil will present the second part. The agenda for the first part is to give a very high-level overview of switch ASICs in Linux, and then talk about the recent improvements in switch ASICs observability in Linux, namely packet sampling and packet drops monitoring. The correct way to think about a switch in Linux is to simply imagine a server with a large set of ports. In this example, we have a data center switch that has 32 front panel ports that are directly connected to the switch ASIC. And for each such front panel port, a net device is created by the device driver of the switch ASIC. And in addition, we also have a management port that is directly connected to the host CPU on the switch. With this type of switches, the switch ASIC can usually forward a few billions of packets per second, while the host CPU can only forward a few millions of packets per second at most. And the two are connected using a PCI bus that has a bandwidth of only a few gigabits per second, compared to the switching capacity of the switch ASIC, which is a few terabits per second. Packets that are forwarded between the front panel ports are forwarded by the switch ASIC. And as such, they are invisible to the host CPU. They do not traverse the PCI bus. So while we get a huge increase in performance by using this ASIC, we also get a very severe degradation in observability compared to a CPU-based solution, compared to a software switch. The next few slides are going to talk about two mitigations for this observability problem. The first one being packet sampling. So usually, when you have a network issue, you're using a tool such as TCP dump in order to sniff packets from the network interface card. But if you were to run TCP dump on the front panel ports of a switch, you would only see control or exception packets that are specifically trapped by the switch ASIC to the CPU in order to facilitate the correct functioning of the control plane. But you wouldn't actually see the majority of the traffic that is flowing through the port. And this is the traffic that is forwarded between the front panel ports. Now, sending all of this traffic to the CPU for monitoring purposes is suboptimal due to the huge differences in performance between the switch ASIC and the CPU. But instead, we can perform hardware-based sampling or filtering. And this has the added advantages of not impacting the data plane performance, since we are only sending a copy of the packet to the CPU, while the second copy is forwarded as usual by the switch ASIC. In addition, it gives us a pretty accurate representation of the data plane traffic, since the packets are sampled at a constant rate according to the configured bandwidth of the port. This slide shows a high-level overview of how sampling works in the kernel. For the software data path, we have a TC action called ActSample that can be attached to various classifiers, such as the popular flower classifier or the match all classifier. And this sample action constitutes the control plane interface for the sampling operation. And it has various configuration options, such as the sampling rate or the sampling group, in addition to the truncation size of the sampled packet. When this action decides to sample a packet, it sends the packet to the psample module, which constitutes the data plane interface for the sampling operation. This psample module copies the truncated packet into a netlink packet, where it also encodes additional metadata about the packet using netlink attributes, such as the input port of the packet and the egress port. Finally, this module sends a netlink notification to user space. For hardware offload of sampling, we have the same user interface. There are no changes. The only differences lie inside the kernel. When the switch ASIC decides to sample a packet, it sends the sampled packet to the device driver of the switch ASIC, which then sends the packet to the psample module, from which it is sent to user space for monitoring purposes. The user interface for the control plane is nothing special, given this is simply a TC action. And as a TC action, it can be attached to various classifiers, such as the match all classifier or the flower classifier, and it can be attached at either ingress or egress. And you can see that we can configure the sampling group as well as the sampling rate, which is offloaded to hardware. The user interface for the data plane for the consumption of the sampled packet is derived from two main use cases. The first one is ad hoc debugging of a specific problem on a specific machine, usually by kernel engineers, while the second one is monitoring a large fleet of machines, usually by network engineers. And each purpose is serviced by different tools. For ad hoc debugging, we have command line tools such as psample and tshark that I'm going to cover in the next few slides. While for monitoring purposes, we have tools such as sFlow that Neil is going to cover in the second part of the presentation. And given the multicast nature of netlink notifications, multiple tools can consume the information simultaneously. So these are command line tools that we have in order to consume the sampled packets. So we have the psample utility that I previously mentioned. It is available on GitHub, and it can be used to display metadata about the sampled packets, such as the ingress port, the egress port, original size of the packet before the truncation, the egress queue, the occupancy of the egress queue, the latency of the packet in nanoseconds, as well as the timestamp. And this tool can also be used in order to pipe these netlink packets in pickup format to tshark or Wireshark for dissection. And Wireshark has upstream support for dissection of these psample netlink packets. Like you can see in this slide, where Wireshark is dissecting a psample netlink packet, you can see the various metadata attributes, such as the input port and the output port. And you can also see the dissection of the sampled packet itself. In this case, this is a UDP packet. And this is the same thing, but with tshark, which is the terminal equivalent of Wireshark. The second mitigation for the previously mentioned observability problem is monitoring of packet drops. So when packet drops are dropped by the kernel, by the software data path, they trigger the K3 SKB trace point. And we have a module inside the kernel called drop monitor that can register its probe on this trace point and emit netlink notifications to user space with the instruction pointer of where the drop occurred. Since kernel 5.4, this drop monitor module can also send the truncated payload of the packet along with various metadata as part of the notification in a very similar manner to the psample module. But what happens when packets are dropped by the switch ASIC? In this case, all of this instrumentation around the K3 SKB trace point becomes quite useless because packets are dropped by the ASIC and not by the CPU. But luckily, we can program switch ASICs in order to trap these dropped packets to the CPU for monitoring purposes. This slide shows a very high-level overview of how monitoring of these drops happens in the kernel. For monitoring of software originating drops, we have the drop monitor module that registers its probe on the K3 SKB trace point. And this allows us to monitor drops that occur throughout the networking stack, whether it is in the VXLAN module, the bridge module, or the IPv6 module. For monitoring of hardware originating drops, we have a similar trace point called the devlink trap report trace point, on which the drop monitor module can also register its probe. This allows user space to consume the information in the same way, regardless of whether the drop occurs in software or in hardware. The only difference is what happens inside the kernel. So when the ASIC decides to drop a packet, it can be programmed using devlink to send the packet to the CPU, in which case it is processed by the device driver of the switch ASIC, which then reports it to devlink, which then triggers the devlink trap report trace point. And as a trace point, we can also attach a BPF program to it in order to get aggregated statistics. And I will show this in the next few slides. So the user interface for the control plane is devlink, like I previously mentioned, and it allows us to enable certain traps. So in this example, we can instruct the device to send packets that were dropped due to a black hole route to the CPU. And we can also police these packets in order not to overrun the CPU. The user interface for the data plane for the consumption of the information is again derived from two main use cases: ad hoc debugging and monitoring of a large fleet of machines. And for ad hoc debugging, we have command line tools such as the dropwatch utility and DWDump utility that are part of the popular dropwatch package. And we also have T-Shark that can be used to dissect this drop monitor netlink packet. For monitoring purposes, we have sFlow that Neil will present in the second part of the presentation, as well as Prometheus, which is a very popular time series database. And again, given the multicast nature of these netlink notifications, multiple tools can consume the information simultaneously. So this is an example of the command line utilities that we have. So here you can see that the dropwatch utility can be used in order to print various metadata about the packet. So you can see that, for example, this packet was dropped in hardware because it says origin hardware, and it was dropped due to ingress VLAN filter. For software originating drops, instead of the drop reason, you would see the instruction pointer of where the drop occurred. And you can also see the ingress port as well as the timestamp. And the DWDump from the dropwatch package can also be used in order to pipe this drop monitor netlink packet into T-Shark that has upstream support for dissection of these packets. And like I previously mentioned, we can also attach a BPF program to this trace point. And using this BPF program, we can get aggregated per trap, per flow statistics. These statistics can be exported from the BPF map to a time series database such as Prometheus, and then visualized using Grafana. This concludes the first part of the presentation, and now I'm heading over to Neil that will present the second part.
Hello, I'm Neil McKee. I'm a developer on the host sFlow project, a user space. It's an open source implementation of the sFlow standard for monitoring network traffic. sFlow defines measurements for real-time monitoring of all network devices, including both switches and servers. The measurements are structured so they fit together in a simple model, and the same standard metrics can then drive a diversity of analytical tools. Now, the focus is on lightweight, continuous monitoring that's robust under all conditions. So in this talk, we'll show how the convergence on standard Linux APIs is transforming and simplifying this requirement for comprehensive observability. I'll describe 3 different measurement mechanisms that stream together in one sFlow feed: periodic counters, randomly sampled packets, and packet drops, and show how they can now use standard Linux APIs that are now the same on both switches and servers. So the Linux kernel maintains detailed network counters exposed via netlink ethtool and /proc. And host sFlow takes advantage of these standard APIs to stream the counters to the sFlow analyzer. sFlow defines standard structures for sets of related metrics. So for example, the switch port counters report frames, bytes, errors, and discards, while the optical interface structure adds transmit and receive power for each SFP in its optical lanes. These structures are encoded in extensible data record format, or XDR, which was designed by Sun for RPC and NFS. And sFlow is designed for real-time monitoring, so UDP transport is used for low latency, and the protocol is tolerant of packet loss under high load conditions. These counters allow the sFlow analyzer to trend link utilizations and detect congestion, but to understand what might be causing the congestion, more detail is required. Who is generating the traffic? What path is it taking? This presents a challenge when the counter may be representing billions of packets per second from a large number of sources. So a good solution for this challenge is to use packet sampling. sFlow defines a mechanism for 1-in-n random sampling, annotated with metadata such as the ingress and egress port, egress queue depth, transit delay in nanoseconds, and details of the routing decision. Support for this sampling mechanism is built into most switch ASICs, and the ASIC driver now exposes this capability as part of the Linux TC subsystem. So the host sFlow agent simply configures the TC filters on each switch port to enable reporting of random packet samples via the psample netlink channel. And these samples are then XDR encoded and streamed to the analyzer immediately, where they're decoded to extract dozens of fields such as source and destination IP addresses, service ports, and tunnels. And the result is a detailed breakdown as shown in this up to the second chart. This level of detail can drive many applications. For example, real-time detection of large flows allows denial of service attacks to be characterized and mitigated in less than 1 second. I'll talk more about that example later. Packet sampling is very effective for understanding network traffic flows, but that's the traffic that's flowing successfully. What about network issues that prevent traffic from flowing? So to troubleshoot packet forwarding failures, sFlow also defines a mechanism to report dropped packets. Support for this mechanism is built into some current generation network switch ASICs. And the ASIC driver also exposes this hardware capability, this time via the drop monitor netlink channel. The host sFlow agent opens the drop monitor channel, and the header of each drop packet is passed up along with its drop reason. Just as with the packet samples, the host sFlow agent XDR encodes and sends them to the collector immediately. Rate limit is applied to protect against the sudden appearance of a large flood of drop packets. The sFlow analyzer then decodes these drop packet headers to report the location, features, and reasons for packet drops anywhere they occur in the network. This can be used to detect and characterize many failure conditions such as black hole routes, microburst buffer overruns, and MTU mismatches. Starting from drop packets and working backwards can transform troubleshooting. It makes it surprisingly easier than it used to be. These three measurement types, counters, packet samples, and drops, work well together and complement one another. So next we'll look at how you configure a system like this. Here's a typical host sFlow configuration that uses the default sampling rate policy, which is shown in the table on the right. And adopting a policy that scales with link speed allows the host sFlow agent to run with the same config file on every switch in the network. Ports are selected for TC configuration using a regular expression pattern, and that also triggers counter export for those hardware switch ports. There are some other modules listed here. The systemd module adds counters to break out the server, CPU, memory, and disk I/O by C group, and there are modules available for Docker and KM monitoring too. But note that with just a couple of very small changes to this config file, you can have the exact same config file for every server in the system too. The only difference being that now you're getting kernel-based packet sample drop reasons with the skbuf drop monitoring point. And the Linux are the same in both cases. So let's take a real-world application. This slide shows an example of using sFlow to detect a service attack. The DDoS controller on the right is programmed to detect UDP amplification attacks. When an attack is detected, specific attributes of the flow, such as the target IP and UDP service, are used to create a mitigation filter, which is immediately installed on the switch. And in this example, a simple Python script provides remote configuration of TC filtering. TC offload pushes the filter into the ASIC for hardware filtering. The chart shows two attacks. The first is not mitigated, And for the second, the controller is enabled and the attack traffic is selectively eliminated before it even ramps up. Just a little note to this: in production networks, BGP is the expected control plane protocol. The controller peers with the router and can push remotely triggered black hole routes and BGP flow spec filters to mitigate attack traffic. FRR is shown in this diagram. It's a widely adopted open source routing application, and currently black hole routes are propagated as expected, but FRR does not yet push flow spec filters into hardware. So I wanted to talk a little bit about my experience of using these new APIs. In my experience of porting the host sFlow agent to multiple platforms over many years, I have noticed a huge difference between almost Linux and pure Linux. When in a situation where the switch NOS has to be a particular distro or include extra drivers, then collaboration with the vendor takes much longer and is difficult to maintain going forward. Sometimes counters have to be read from a non-standard API, or packet samples bubble up in a different place with a different format. And every change to those APIs leaves host sFlow out of date. Sometimes debugging has to happen over Zoom with a vendor engineer in a noisy test lab many time zones away. But on the other hand, when all the APIs are standard and stable in the Linux kernel, then I can build, debug, and troubleshoot on my laptop on a VM and know that the behavior will be the same on the vendor switch now and on any future deployment. And it's not just easier for me. The fact that these APIs are already in the kernel, it kicks off a cascade of advantages down the line. For network engineers deploying these solutions, the fact that they can choose to run the same Linux distro on their switches as they run on their servers is potentially a big step forward. And the choice to add only the tools and features required for how they run their network allows for a minimal footprint deployment, which is easier to maintain and secure. For me, this feels like one of those breakthroughs where we look back afterwards and wonder why it was ever done differently before. So hats off to the Cumulus and NVIDIA and Mellanox teams who saw the potential for this and made it happen. So at this point, we're going to turn it over for 15 minutes of Q&A.
Perfect. And we are back. Thank you, Neil. Thank you, Ido. We have a few questions, so we'll go with that. So let's start with this guy. You guys can see it, right? And respond if you can.
Yeah. So the limiting factor is not really the interface between the kernel and user space, but rather the bottleneck that we have between the ASIC and the CPU. I mean, the ASIC can drop billions of packets per second, and we can only send very few to the CPU. I mean, we have both the PCI as a limiting factor and the CPU itself that can only process a few millions of packets per second, because these CPUs on the switches are usually very low end compared to what you see on servers. So Netlink is not the limiting factor. And we also, like I showed I think in the last slide, we can do aggregation inside the kernel in order to only give you aggregated statistics, like per drop reason, per 5 tuple statistics. So there is very low traffic between, I mean, you only need to read a BPF map. You don't need to send the entire packet to user space.
Jamal wants to join in and say something to that, Ido. Jamal, you're on.
Yeah, this question is more for Neil. Hi, Neil. So with current approaches, for example, if I look at the DX6, ConnectX-6, I'm sorry, from Mellanox / NVIDIA, if I can keep track of 16 million flows in a NIC, why do I need to sample? Because all these flows have counters. I'm questioning the need for sampling. You show 30 seconds, and you only get a small subset of the flows that go through.
The use case for sFlow is when you're monitoring hundreds of switches, maybe thousands of switches. And the accuracy of the traffic matrix data you're generating is dependent only on the number of samples you receive. And for most applications, with being plus or minus 1% is accurate enough. So the reason you don't try to sample every packet is that you don't have to. It's it just destabilizes the system if you try to boil too much. There may, of course, be other applications, though, where you do want to be able to do that. So this specifically for whole networks monitoring with sFlow, you actually want to sample as sparsely as you can get away with. And it turns out that you really can back it off a long way and still get good data.
Okay. We will move on. Actually, we will go back to the original question, the previous question, which I thought Jamali wanted to jump in on, which is kind of related, right? It is all about downsampling. So I would actually, I would disagree that netlink to user space is not a problem. I agree. The bigger problem is getting hardware into the CPU. But if you actually had the ability to get that at pretty high rates, then the next problem would have been the netlink to user space as well. But let's ask the question instead. So let me go to my question, which was, and I see your answer, but it's like the same real system, right? So the problem that this model introduces, and obviously we ran into this in Cumulus a lot, is every device out there has a different strategy, and literally every device has a different strategy on how they report errors, stats, counters, blah, 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 right? Some DMA them, some compress them, some do bit vectors, all kinds of different things. The question is how much effort has been put in to try to create consensus between people as to what is the good middle ground. And I suspect Neil may have something to say here as well, because independent of what you were saying about the complications you had with trying to get different platforms to play with you, you've had to talk to every platform vendor out there. And I mean, this is a hard problem, right? Like there's no easy way to solve it. But is there momentum? Are people saying that, look, we'll come up with some basic set of events? Because unless you can do that, while it looks really nice on the spectrum, and I know the spectrum can do it, and I know you put in the effort, and it can tell you that this was a drop because of VLAN, some other switch, some other device, some other exotic infrastructure may not be able to do it. And since the other things you said that support it are effectively a NIC and a programmable CPU and NPU, really. Yes, they find it easier, right? But it's the other high-performance devices, ASICs, that's going to be where the problems live.
Yeah, so I want to touch on the first comment about netlink. So yeah, it can be the limiting factor. It currently isn't, but we also have the ability to run BPF programs. And these BPF programs can, for example, all the map of all the flows that they have seen until now, and only send unique copies to user space via a BPF ring buffer, for example. So this also reduces the traffic between user space and kernel. Regarding the commonality, so a solution that would fix the performance problem is just, instead of sending these packets to the CPU, just send them to a remote server, right? Mirror them to a remote server where you're doing all the analytics instead of the host CPU. But the issue is that each vendor has a different proprietary way to encode the metadata inside these packets. And there you cannot get any commonality. There is no like RFC, there is no standard. So getting it to the CPU allows us to create to abstract these differences between vendors and only standardize the interface between the kernel and the CPU and the user space, where the kernel is doing the abstraction over hardware. And regarding the commonality of the drop reasons, so we try to stick to logical drops. Like every switch is going to have a trap for unresolved neighbor because they need it for ARP resolution. And like Inger's villain filter, I think it's very common. And on top of that, we also have grouping, where we say layer 2 drops, layer 3 drops, based on where they occur in the pipeline, because switch ASICs usually have these nice pipelines. So this gives you another level of abstraction for individual drop reasons. So you can look at that and get some commonality instead of only individual reasons. Yeah, basically, we do not have some RFC to standardize all this stuff.
That's actually where I was going. I think, like you said, well, TAP is a very spectrum way of doing things. There are other, again, that may not apply everywhere. But I think the point I was trying to make was it may be, given the value becomes pretty easy to prove, it may be a good idea to float an RFC and see if people sign on, right? Because then at least you get to say, and I hear what you're saying and saying that you can, if you let people come up with the reasons and the driver is theirs, they can sort of abstract it within themselves and you've only standardized the interface of that. But it may be worth floating an RFC just to see. Right?
Yeah.
The value is clear.
I think that the main problem is that usually hardware vendors, they are like racing to get the latest hardware as quick as possible. And like even before you have you can have VXLAN support. You had VXLAN support in ASICs even before it was completely standardized. So you have these different hardware implementations. So I'm not very hopeful that we can do it, but maybe.
I hear you, but trust me, I was there when that VXLAN war happened. But the point I'm making is this, right? So in the way you guys are doing it right now, I think I'm actually more hopeful, because if the RFC really says put a reason code here and do something interesting, right? But normalize or put an enum of the reason codes and it gets loaded into a user space driver or the user space handler, it may be something that you can come up with. At least standardize the transport of the message. You don't have to standardize the message itself and let that be programmable, right? I mean, if you do nothing other than just that, I think you'll get a huge leg forward or a huge step forward. But obviously, since you have to do the work, it's your feeling that matters. Anyway, we are. Do we have any more questions? I don't want to completely bogart. So no more questions that I'm seeing. Any? Okay. Well, in that case, we will thank Neil and Ido, and good job.
Thanks.
Thank you, everyone.